Yo, what up, y'all? Welcome back. In this video, we're going to continue our conversation about how to translate the coupled pendula problem into a standard eigenvalue problem. Specifically, we're going to talk about how to mathematize this problem. When we mathematize the problem, what we mean is turn it into mathematical symbols and equations that capture the relevant features of the problem we're trying to solve. For students in my class, I'm going to give you access to a separate playlist that gets you ready to do lab work on a McCusker apparatus. I'm going to bring one into class. You'll have time to play with it, to set it into motion, to capture video using your iPhone or smartphone, and then import that video into Tracker. In this video, though, we're going to focus on observing some of the features of the McCusker apparatus that are most relevant to mathematizing this problem. Let's start our exploration by looking at a schematic describing the McCusker apparatus. You see that schematic on the left-hand side of the screen. On the right-hand side is an ideal diagram of the components that are most important for the mathematical model. When we actually build one of these apparatus, some features come into play. First, the rods that define the ideal pendulum are created using thin wire, almost like the wire used on a bike for the brake cables. That wire actually comes down in through a small particle board that's cut very thin, and then up through the other side, hanging off a stable structure. On top of the particle board, which Mike calls a sled, we place masses or weights. A creative use of those masses or weights actually combines small weights used in a free weight gym with small containers filled with sand so that the two masses can be designed to have identical mass measurements if desired. In the ideal diagram, notice that we're thinking about each of these masses at a point mass, where in the actual apparatus, the masses are distributed. There are small center of mass calculations that we'll do when we actually do our modeling problem to allow us to figure out how long from the point at which the cables are attached to the center of a mass horizontally is that value L. When setting up an eigenvalue experiment, we attach a camera from the top-down view so that it actually films from above the movement of these masses. Moreover, we put a black dot in the center of the mass on above so that the camera picks up that black dot. Finally, we move one of the masses along this direction, labeled here as the direction of traveled. Over here, we see that direction actually has a metric ruler assigned. Once we've moved that mass, we let both masses swing freely and we capture the dynamics from above. We capture the movement of the center of masses using our camera from above. From the standpoint of the mathematical model, what's important is that these cables act as a stiff rod. They do not bend and buckle. That the masses move in small angle approximation. In other words, these are not wild swings, but very small swings around the center of the resting mass. Third, that the spring acts as an extension spring. So there's never a time where the masses get so close together that the spring coils touch each other and turns into like a solid cylinder, and instead it always a little bit extended. And then last, that we're not losing a ton of energy to the support structure. Another way to say that is that the structure itself is quite stable. There's not a lot of vibrations in the structure. The only things that's shaking back and forth are the masses. One of the beautiful things about Mike McCusker's design is that he captured all of those specifications at a very low cost. I think he made his for something like 40 or 50 bucks. And we could actually capture the fundamental quantities needed for the mathematical modeling as the length of each rod, the spring constant in the spring, and then each individual mass. And that's all we'll need in order to set up our entire mathematical model. To bring this point home, let's take a look at a side angle of the McCusker apparatus that I built. Then we'll look at a video of a mixed mode oscillation of an eigenvalue experiment shot from above. We'll start with the side view of the real apparatus in action. There we have it. This thing's ready to go. This is an eigenvalue problem maker. Check it out. I can go ahead and put it in the mixed mode, then normal mode 1, normal mode 2, and we're ready to go. Here is a bird's eye view of the motion of the masses. This camera is attached to the top of that structure shooting downwards. We see that the center of each mass is marked with a black dot. There's a ruler attached at the bottom of the screen, and that ruler actually has some marks to say those two blue marks are 10 centimeters away. Then we see that the spring always acts in extension. Notice it never gets close enough to the other mass so that it turns into a cylinder. This is really interesting. If we see the motion in the mixed mode, this has two different things going on, which we'll see later. The energy is kind of transferring from one mass to the other. Do you see that? So here the right mass is moving, mass 2 is moving, and then all of a sudden the spring transfers that energy over to mass 1. Mass 2 stopped moving. The question that we're going to ask ourselves is, if we were to think about that center of mass as being positioned along this ruler, the claim is that we could actually map out that position over time and it would create a mathematical function. And our question in the coupled pendula problem is, can we get an explicit description of that function? Let's take a look at an ideal representation of this problem that I created in Mathematica. The point of the image that you see is to slow things down a little bit and let us play with parameters. I hope that in doing so, we can get a very accurate idea of the problem of trying to describe the displacement of the masses using functions. In this case, what we've done is we've rotated the masses so we get a side view of this. The red mass will be the left mass in the video, the blue mass will be the right mass, and then we see that we have a metric ruler on the left-hand side. What we can now do is kind of play around with the initial condition, so I can change the location of the left mass. Imagine that I pushed the left mass towards the right mass to start with. And then the question is, well, what happens over time? And indeed, what we see is there's this function behavior. Check that out. I can actually play this over time. Changing the initial position of my left mass changes the way that that actual function plays out. Now, if I don't perturb either of them, that's called stable equilibrium. There's no displacement. It just stays where they are. But if I displace one of the masses to begin with, in this case I've moved the mass 1, the red mass, towards the right mass to begin with, and then we see that over time these masses move back and forth, and there is this energy transfer. See, when this energy is low, when the mass is moving around that equilibrium position, this one is high and back forth. The question is, well, what happens when I move either one? And check this out. There's this really interesting thing. If I were to move both masses, so let's go ahead and restart this. We see under the original condition, if I don't displace either mass, I have no change in displacement, and my position functions are really boring. They're constant. If I change the position of one mass, let's say that I move the right mass away from the left mass, there's this really, really complex behavior where the energy is being transferred from the right to the left and back and forth. And you kind of see that over here. In fact, I can up the spring constant. Yeah, there it is. Do you see that? When I have large oscillations in the right mass, I have small oscillations in the left mass, and then vice versa. So there's this energy transfer. One of the claims I'm going to make is, what if I were to actually displace both masses the same amount in the left and the right? Look at that beautiful structure. Doesn't that look like a cosine curve? And in fact, this is a demonstration of what we're going to learn later as called the first natural frequency of the system. The period of this frequency from peak to peak, the period of that cosine curve, is very much related to the first eigenvalue and eigenvector of this system. On the other hand, if instead of moving both masses the same amount, so I'm pushing both masses here and then they just swing as a normal pendulum would swing that's not connected by a string, if I were to push the masses away from each other the same amount, in other words, I displace the right mass by, in this case, positive 0.1 meters, and I displace the left mass by negative 0.1 meters, notice these are anti-symmetric. They move towards each other and away from each other. Towards each other and away from each other. This is called the second natural frequency, or the second mode of this system. It is also directly connected to the second eigenvalue and eigenvector pair of the associated matrix model. This anti-symmetric motion stands in contrast to the symmetric motion. Notice that when we displace the left and right mass together, they move as a pair. So literally they're just moving as a kind of coupled set of pendulum. And the claim that we're going to make is that when we move one mass a little bit and move the second mass in a different way, the function that gets out of this is going to be related to something called a linear combination of eigenstates. Now, I'm stealing your thunder a little bit. The point of this, though, is in this diagram, what we're seeing, the goal of the coupled pendulum problem is actually to come up with a function definition, like describe this thing in terms of sines and cosines, probably because it looks periodic. Can we come up with an explicit definition of what this function is, only knowing the spring constant, the masses on each sled, and then also the length of the pendulum? Of course, our solution has to take into consideration the initial position because that very much affects the dynamics. But that is the coupled pendulum problem, trying to figure out the motion of those masses under different parameters and come up with an explicit function to describe that motion.